We're now going to introduce a method for geometrically representing a complex number. In addition, we're going to learn how to write a complex number in polar form. Let's first start with geometrically representing a complex number. When we do this, we first need to remind ourselves that a complex number is a number z equals x plus yi, where x is called the real part of the complex number and y is called the imaginary part. What we do is we plot x as the point that corresponds to the real axis, and we plot y as the y-coordinate corresponding to the imaginary axis. So x is the signed distance from the imaginary axis, and y is the signed distance from the real axis. We're now going to talk about how to represent a complex number in what's called polar form. Let z equal x plus yi be a complex number. The magnitude or modulus of z, denoted by the absolute value of z, is defined as the distance from the origin to the point xy. Thus, the magnitude of z is the square root of x squared plus y squared. In other words, the square root of the imaginary part squared plus the real part squared. So we have labeled here a geometric understanding of what the magnitude measures. It's just the distance from the origin to the point in the complex plane. Recall, if z equals x plus yi, then its conjugate, denoted by z bar, is z bar equals x minus yi. For that reason, z times z bar is going to equal x squared plus y squared. In other words, we can find the magnitude of z by taking the square root of z times the conjugate of z, z bar. Now what we're going to do is learn how to represent the complex numbers in polar form. Recall that x equals r cosine theta from the polar form of a number, and that y equals r sine theta. Therefore, z equals x plus yi can be written as r cosine theta plus r sine theta I, where theta is the angle between the real axis and the terminal side of the segment drawn from the origin to the point in the plane. So we have that z equals r times the cosine of theta plus I sine of theta is the polar form of a complex number. Let's look at an example. We're asked to first plot z equals the square root of 3 minus I. We recognize that this is the square root of 3 minus 1i. So the real part of the complex number is the square root of 3. The imaginary part is negative 1. To plot the point, we go square root of 3 units to the right of the imaginary axis to about 1.7, and then down 1 unit. So the complex number z in the complex plane is located in this area right here. Now what we want to do is write this number in polar form. To do that, we recognize that we have z equals the square root of 3 minus I. What that means is that we first need to find the value of r, which is nothing more than the magnitude of the complex number. Remember, that's found by taking the square root of x squared plus y squared. Well, the square root of x squared is going to be the square root of the square root of 3 squared plus negative 1 squared. I get the square root of 3 plus 1 is the square root of 4, gives me 2. So the magnitude or modulus of z is 2. Now what I need to do is find the angle theta, where theta is going to be a value between 0 and 2 pi. It helps to remember what the graph of this particular point looks like. Remember, the point was right over here in the complex plane. So what we're looking to do is find this angle right here, theta. How can I find that angle theta? Well, remember, the sine of the angle theta is going to be equal to the y coordinate, which is -1 over r, and the cosine of the angle theta is going to equal the x coordinate, square root of 3 over r. So all we need to do is think of an angle theta whose sine is -1/2 and whose cosine is the square root of 3 over 2. You should be reminded, or you should remember really, that theta would be equal to 11 pi over 6. So we would have that z equals r times cosine of theta plus I sine theta, where r is equal to 2, and then we have the cosine of 11 pi over 6 plus I times the sine of 11 pi over 6. So that is the complex form, that is the polar form of the complex number.